Okay, and from that point we will start from current slide. Okay, any questions on anything we've done so far? Gotta find my pen here. Any questions, issues, concerns, problems? Okay, I probably need to say this later when more people are here, but I want to go on and get it said now so I make sure I don't forget to say it at all. You know what next Tuesday is, right? Election Day. Yeah, okay, good deal. I hope that all of you are registered to vote, or at least all who can be registered to vote are registered. And if you are registered, that if you haven't voted already, my wife and I voted back in September, in fact, but if you haven't voted already, please, please, please plan to vote on Tuesday. Even if that means you have to miss a little bit of this class, that will be okay. I'll try to be recording everything. Just get back here as soon as you can. If you can vote without missing class, that's even better. But I'll be recording hopefully everything. So if you do miss something, hopefully you'll be able to pick it up on the YouTube videos. All right, so I'll try to say that again before the end of the day in case other people come in. Hopefully they will be coming in. Now let me make sure that no one else has tried to come in while I was talking. Nope, we still got 7 seated. 1, 2, 3, 4, 5, 6, 7. Got it. Okay. So, okay, I don't know what that is. Okay, but if someone's trying to chat, go on and get it out unless you feel like. See, if I pull it up, everybody can see it anyway, I think. So, anyway, if you do need to communicate, communicate. All right, we are in chapter 3, the energy chapter. We have been talking about work, and we talked about this pretty much ad nauseum last time, but I believe we're on page 65, the top of the page there, example 3.1. Now it's beginning to warm up a little in here. It was getting cooler outside, but now it's beginning to warm up some, so let me turn on the ceiling fan and we'll go from here. All right, if there are no questions, we're on example 3.1, top of page 65. Okay, now it says here how much work. Any questions? Planning to, if we get far enough along in class. I think we will be. I don't think it'll take the full 2 hours, but I think we will get a significant amount of lab done. I put it out there under, what is this, week 3? The same link, the one we've used before, we're still using, and the lab printout will be is there as well. Okay, it's called the Energy Skate Park or something like that. Okay, so that's the one we'll be doing today. All right, any other questions? All right, example 3.1, top of page 65. How much work? So we're looking for work here. If I can get my pen to show up here. Where is my pen? I don't see it any. Oh, there it is. Okay, we're looking for work. Now capital W is usually work. This is what we're looking for. And again, the pen is nowhere. There it is. That's what we're looking for. Is needed to lift a 5.0 kilogram backpack. Okay, so what in the world is 5.0 kilogram? What does that measure? What's that a measure of? The mass of the mass of the backpack. Okay, to a shelf 1 meter above the floor. So what is 1 meter measuring? If I could get my pen to show up here somewhere, there it is. 1.0 meters above the floor. What's that a measure of?
Is it length?
Length or distance, either one. So I'm going to call it D because I think that's what the book calls it. Okay. Now, can we calculate work based on those two pieces of information? what is work? Let me go back a slide or two. There it is. Work is equal to force times a displacement. Okay, so there's the formula we'll be using. Work is equal to force times the displacement. So I thought they did use D. Okay, a problem here though, we don't have force, we have mass. So what force are we dealing with if you're lifting a backpack off the floor up to a shelf 1 meter high? What force are you dealing with? Okay, there it is. Your force here that you're dealing with here is the weight of the backpack. Now I hesitate to use weight because it's little w and you might get them confused, but I cannot find, there it is. Okay, my pen disappears on me. The weight here is the force due to gravity. Okay, I'll call it W sub G. And does anyone remember what that was? We hit it just a few pages ago, I think. No, in chapter 2. Chapter 2 we talked about what weight is. Weight is mass of the backpack, times the acceleration due to gravity. Okay? And since we're on the earth, that's a constant. So this force, or weight, is 5.0 kilograms times acceleration due to gravity, 9.8 meters per second squared. Okay, that gave us a force of 49, I believe it is. I'm doing it in my head. 49 kilogram meter per second squared, which would be newtons. Does everybody see that? Okay, now that we've got the force, we can plug that in here. So the work done, this is capital W for work, is equal to force 49 newtons times the distance displaced 1.0 meter. That's going to be really easy to multiply, and this will be 49 Newton meter, which are joules. So it should be 49 joules. Any questions on that? Do you see how that works? Okay. Now, with that done, does anyone else need this left a little bit longer? Everybody okay with it? Okay. Let's clear the screen then, if no one has any questions. Okay. 3.2, near the bottom, near the middle of the left-hand column on page 65. How much work? So again, we're looking for work. I could get my pen to show up somewhere here. Come on, pen. There you are. Okay. There we go. How much work, again, we're looking for work, is required to lift a 50-pound box? Now, what does 50 pounds represent? 50 pounds. What does that measure? That is, you're absolutely right, weight. Now that's little w. Capital W is work. I'm going to call it weight due to gravity. Okay, that's what gravity is. Okay, but I'll put that as a. That is your 50-pound box. You're lifting it vertically a distance of 2 feet. So there is your distance, and that distance is 2 feet. Now, they don't say 2.0 feet, they just say 2 feet. Okay, well, what is work? Just like we had before, work is equal to force times a displacement. Now remember, the force and the displacement have to be collinear. You're lifting straight up, the displacement is straight up. So yes, that works well. So you plug in If I could find my pen, there it is, I think. Yeah, there it is. Your force was 50 pounds. I don't know what the little noise is. Times 2 feet. And that multiplies to be 100 foot-pounds. And that's a legitimate measure of work in the U.S. customary system. Joules in the SI system, foot-pounds in the U.S. customary system. 100 foot-pounds. All right, and that's what they got to. Good for them. Any questions on those two exercises, examples? Okay, now I'm going to put my pen aside for now, and let's get back to the PowerPoint. Okay, now this is not an example, but it could have been. Okay, here we have a book down here on the second shelf, not the bottom shelf here. The weight of that book is straight downward. So in order to lift that book, you have to lift straight upward. Now you do have to pull it out of the shelf a little ways to lift it up, but pulling it out of the shelf is perpendicular to your weight. You're not really doing any work there. You may feel like you are, but you're not. But once you get it out of the shelf, then you have to lift it up and put it up here on the top shelf. So the force, which is the weight of the book, times the distance that you lifted it, that is your, where did it go? Okay, that is the work done. Force times displacement, as long as they're in the same direction. Okay, and these are. So that's an illustration of work. This is the figure, top of page 64, figure 3.3. Any questions? Okay, now they jump a little bit here and go over to simple machines. Now the simple machines are illustrated on page 66 and 67, the top probably 2/3 of those two pages. This is an interesting thing to do and to talk about, but it sort of breaks the continuity of what we were just doing in the class. But let's hit it. Okay, now with simple machines, if you remember, we said energy is always conserved, and one form of energy is work. So work technically is always conserved. Okay, now another way of saying that, the work you put into a system has to equal the work you get out of the system. Work in equals work out. Now, I have a dumb question for you. Can any of you lift a car? Yes or no? No, you don't think you can. So you've never had a flat tire, have you? Yes or no?
Oh, that was smart. Yes.
Yes? Well, what did you do to get that tire off?
That's true.
You used the jack and you lifted the car. Maybe not completely off the ground, but you lift it. Okay? Here's the deal. What you had there was something they call a force multiplier. And the force is multiplied by the ratio of the distances through which you acted. Okay? Because when you were jacking up that car, think about that. Your hand went up and down, your arm went up and down a pretty good distance. Okay? You were applying a force when you were pushing down, okay, but you went quite a distance. You only lifted the car maybe a little bit, but that force multiplied by the ratio of the distances. If you went up and down 50 times the amount that the car went up, that's your 50 times force multiplier. So yes, you did lift a car, okay, but you lifted it because you used the ratio of distances. That jack was an example of a simple machine. Okay, now here's several others. I have done this before. I can't think right now specifics, but we've moved several times, and if I had a heavy piece of furniture, maybe a refrigerator or washing machine, something like this, and I was having to load that on the back of say a U-Haul truck, okay, I can't lift that refrigerator. It would be really, really difficult. But I put it on a dolly. The dolly had wheels on it, and I put a ramp up to the back of the U-Haul truck. Okay, now did I have to lift the entire thing up? Well, in reality I did, but what I did, I went up the ramp, so the distance I went up was far further than the ground to the truck. Okay, well, by doing that, I had a force multiplier, the ratio of the distance I pulled it up on the slant compared to how high I lifted it. That was my force multiplier. That's called an inclined plane. That ramp was an inclined plane, and I was able to roll the dolly with the refrigerator on board up the inclined plane. Way easier than trying to lift the refrigerator or the washing machine or something manually and put it on the truck. I used the inclined plane, which had a force multiplier, the ratio of the distances. Now, have any of you ever split firewood? I don't know that you have, but just wondering if you have. When I grew up in Georgia, we had fireplaces and later a wood stove, and we lived on a farm, had lots of wood, and every winter that was pretty much a weekend job, was getting out there cutting firewood. And if the firewood was really big, we would split it because the really big chunks were hard to burn. Well, did I take my fingers and yank that wood apart? No way. What I used was a wedge, or my dad used a wedge, or my brother used a wedge. You get that going, hit on the wedge with either a hammer, an axe, or a sledge or something like that. Pressed on that wedge, and the wedge drove its way in between the wood. You have to put it in the right place, of course, pushing it apart. What you had there was two inclined planes, one on one side, one on the other, hit on the top, and it forced that apart. You hit down with the wedge, with the axe or the sledge, hit down a large distance, moving apart the wedging that piece of wood just a little difference. That difference, the force multiplier, the ratio of the difference, was enabled you to exert a lot bigger force on that wood than you would have trying to pull with your fingers, which you couldn't have done anyway. Now, don't know if any of you, I imagine you have used a screw to tighten something down. Well, think about what a screw is. That's an inclined plane wrapped around an axis. Okay, my phone's ringing. Let me see what this is about. Nothing that I can tell. Okay, let it ring. Okay, sorry that I have to have the phone in here, but every now and then I have students not able to get in class, so I want to have my phone here in case I can see. Let me just see if anyone's waiting. I don't see anyone. We still have the 7 people we did to begin with. Pretty low attendance today. Hopefully more will be coming in. So what is a screw? A screw is an inclined plane wrapped around an axle. Think about that. That's exactly what a screw is. You're using the advantage. You turn and turn and turn with the screwdriver, moving a great deal of distance that way, but it only goes a little bit into the wood or into the metal or whatever you're doing into, but it's a very strong force because you have the force multiplier as the ratio of your distances. Now your jack, that was an example of a lever. Okay, you went up and down with the handle large distances, the car went up just a little distance. Okay, but that's a force multiplier, the ratio of the distance by which you did. Okay, a wheel and an axle. Okay, think about this one. you're turning in your car engine a shaft. Now, that's a pretty small shaft, maybe an inch or two in diameter. Not that big of a shaft, but it's, a good sized shaft. But your wheel is much bigger around. Well, one turn of the shaft turns this. The wheel is much bigger. The ratio of those distances, is your wheel and axle. All right. Another example, a pulley. Okay. Now, some pulleys don't give you much of a force multiplier at all. If all you're doing is pulling down on something, lifting something up, that's just a change of direction. It's not really a force multiplier. However, if that pulley goes up, down, and up again, okay, then you pull twice as far to lift half as far, you have a force multiplier of 2. Okay, and I don't know, I think I've asked this question before, but I'll ask it again. Have any of you ever been to the McWane Science Center? Anybody? A good place to go. All sorts of interesting things there. There is one device. Say again?
My child loves it.
Oh, I bet so. Every chance you can. Interest him or her in science. It's just great to do. There is one thing there. It has a 3-station thing, and you sit on a little seat and you pull on the rope on a pulley. And the first one of those, all it does is go over the top. You're trying to lift yourself, and unless you are very, very strong, that's a hard thing to do. The second seat, though, goes up, down, and up again. So that way you pull twice as far, and it's much easier to lift yourself. You don't lift yourself as far, but you can lift yourself. The third one goes up, down, around a couple of times, and in this case, you are lifting yourself only a quarter of the distance you pull, and you can just pull yourself right on up there. That's an example of a pulley. When it just goes up and over, force multiplier 1. No mechanical advantage at all. When it goes up and down twice, force multiplier of 2. With half the force, you can lift your entire weight. And the other one, when it goes up and down a couple of times, then you can lift 4 times your weight. Of course, you're pulling the rope 4 times as far as you're lifting, but it's much less force. Those are examples of simple machines. Let's see if we can get the PowerPoint to come up. So here is your basic premise here. Work in, the force that you exert going in times the distance you pull it going in is equal to the force out times the distance out. When you're jacking up your car, your force may be only 50 pounds or something like that. The distance in may be several feet. Okay? The force out, in other words, how much weight you're lifting on the car could be several tons, but you're only lifting it a very small distance. So what you do is divide both sides here by dn. No, let's see. D out, I believe it is. Let's see how they do it. Yeah, divide both sides by D out. The force, the output force here is that ratio of dn to D out times the input force. So if you say did 50 pounds here, but your dn, the ratio of your input, let's just call it 50 again, divided by output, let's just call it 1. Okay, so 50 times 50 is 2,500. So you get a force out. You can lift a 2,500 pound car with only 50 pounds of force. That's the advantage of a simple machine. Now they call that ratio the mechanical advantage. I don't know if this book calls it that, but that's how I always learned it, the mechanical advantage. You're doing the same work, work out equal work in, but you're alternating the amount of force in and out by the ratio of the distances in and out. Okay, here's a gal, okay, she's pushing down with 60 pounds of effort force, okay? Now, her effort distance is 2.5 feet. Over here, she's trying to lift 300 pounds. Now, does it look like that skinny little woman can lift 300 pounds? I don't think so. But if she puts up her lever here, this is a lever, put the fulcrum here, and the effort distance is 2.5 feet, she's only going to lift that half a foot. Well, that's a 5 times the ratio. So with 5 times 60, she can indeed lift 300 pounds. No matter how skinny her arms are, if she can do 60 pounds down, she can lift that 300 pounds up. But it doesn't go as high. She pushes down 2.5 feet, it only goes up half a foot. That's your force multiplier. The ratio of the distances, 2.5 divided by 0.5, that's a 5-to-1 ratio. Multiply the 60 pounds input by 5 and you get 300 pounds output. That's your simple machine. One of them, a lever. Now, before we get to power, there is at the top of that page 67, we're going to go back to power, but here is 3 types of levers, okay? Now the first type of those is sort of like a seesaw, okay? Put the fulcrum right in the middle and you push down with a certain force, you can lift up the same amount with exactly the same force. That's like if you're playing on a seesaw, teeter-totter, however you want to call that. That second type of lever, you're pulling up where you see the black arrow there. Your fulcrum is down here. Okay, I may have said that wrong. No, the black triangle is your fulcrum, and the resistive force is the R. Your applied force is that F? I can't read it. Effort force, E, okay? The effort force, what you're doing into it, okay? That type of lever basically is your wheelbarrow. That fulcrum there is where the wheel is in the wheelbarrow. You're lifting your effort force at the end of the handle of the wheelbarrow, but you've got the weight, the resistive force, about midway out there. So you can lift and roll twice as much force, twice as much weight with the wheelbarrow as what you exert, because you have a 2-to-1 ratio. Okay, so a wheelbarrow is the second type of lever. Now the third type here is rather bizarre, but true. Okay, it looks kind of like the wheelbarrow, except here you have the resistive force here, here's your effort there, there's your fulcrum. What in the world is that? That's a shovel. Your fulcrum is the end of the shovel. You're holding that down with your hand. You push, or your effort force is about midway to handle, and you're picking up here. Guess what? That's no mechanical advantage at all. In fact, that's a pretty small. That's you can lift half as much with that as you could with the other. But what's the difference? You can throw it a lot further. And that's what a shovel does. Dip it into the ground, and holding your fulcrum here, your handle here, you can pick it up half the weight, okay, that's fine, but you can throw it twice as far. So in that sense, your force ratio is reversed. The ratio might be 1/2 rather than 2. Well, you don't care because you're going to move half the load, and that spade of the shovel doesn't hold a lot of weight, okay? So you can do half the weight or force but throw it twice the distance. And if that's what you're after with a shovel, yep, that gets it for you. So there's your example of simple machines. All right, top 2/3 of pages 66 and 67. All right, now what we're going to do, advance the PowerPoint, but we're going backward in the book. Go back a page to page 65, and now you'll see the subtopic power. Now, time out for a moment here. I want you to think back to what we've done in physics so far. One of the first quantities that we measured was distance or displacement. Displacement was the vector quantity, distance was the scalar quantity. Okay, once you got a good idea of that, what was the next thing we did? We took the time rate of change of this distance or displacement. That's speed, talking about the scalar quantity, velocity, talking about the vector quantity. Distance divided by time, that's your speed. Displacement divided by time, that's your velocity. Okay, once we got that down, we did it again. Take the time rate of change of your velocity, that gave you acceleration. How fast is the speed changing relative to time? Okay, now also back in chapter 2 we talked about momentum and introduced this. We don't usually think about it this way, but the time rate of change of momentum is force. Okay, time rate of change of momentum is force. So it seems like one of the popular things to do once you got something understood, let's take the time rate of change of that. Well, what have we been doing most of this chapter so far? Work. The rate at which, the time rate of change at which work is done, or the rate at which energy is transformed. Remember, energy and work are both energy forms. Okay, that's called power. Power is equal to work divided by time. That capital W, remember, is work, not weight. Work divided by time. That's what power is. Now here is a good old example. This is a good old strong dray horse. This is a pretty powerful animal. He can lift 550 pounds. Okay, he can lift that 550 pounds 1 foot in 1 second. Now, guess what power we call 550 foot-pounds per second? Work is measured in foot-pounds, time measured in seconds. 550 foot-pounds per second. Guess what that's called? What is this animal here? Horsepower. That's exactly what we mean by horsepower. 550 foot-pounds a second. That's 1 horsepower. Okay? Yes? Well, on average, now this is how they determined it. On average, a dray horse working for a full day is going to average 1 horsepower. Okay? Now, certainly, if that horse was fresh and just came up, good night's sleep, eating his fill and stuff like this, yeah, he could probably pull with several horsepower. But to maintain that all day long, that's going to average about 1 horsepower. Now, a little racehorse probably isn't going to get as much. A great big dray horse, think of the Clydesdales that they use pulling the Budweiser wagon. Those are really powerful. They may be actually able to do more than 1 horsepower, especially if you have a whole bunch of them there. They can exceed that. You yourself, I bet, I know I've measured it before, you can probably do more than 1 horsepower, but for a very short amount of time. Okay? The lab that we would be doing today, we're going to describe it in just a few minutes. You'll see if we had been able to do it, if we were on campus, some of you would have measured more than 1 horsepower, but not for very long. Okay? If you average it over a whole day, you're considerably less than that. Okay? But that's a very good point. Now, let's go to this. Power is the rate at which work is done. When you see that term rate, think time rate at which work is done. Now, in the SI units, the unit for power is watt. Capital W, okay, now don't get that confused with the parameter for work, which is also capital W, but what this is the unit, capital W, because it's named after James Watt. Now, James Watt was a Scottish physicist and engineer, and he did a lot of the early work with power, and so they named the unit after him. But he was dealing with the British system, not the SI system, but they named the SI unit for work after him, watt. In the US customary system, which used to be the British system, then we use horsepower. Okay, so what is a watt? A watt is joule per second. Now a joule is a pretty small amount of energy, and a second is a very short period of time. Horsepower, on the other hand, is a big unit. That's 550 foot-pounds, which is quite a bit of work, divided by 1 second. Okay, so that's what a horsepower is. 550 foot-pounds per second. A watt is 1 joule per second. A joule is a much smaller unit than a foot-pound. Okay, now here is the example that we would have done if we were on campus. We would have gone to the stairwells there on the Bessemer campus, and you first would have walked up those stairs. You first would have measured the height of those stairs, okay, from say second floor to third floor, okay, or first floor to second floor. They've been about the same. Measured that height, and then timed yourself, or someone on your team would have timed you, as you walk slowly up those stairs. Okay, now, what was the work you would have been doing? Your weight, because that's what you're lifting, your weight times the height that you raised your weight. Okay, so that would be feet with the height, pounds. Oh, whoa, here comes somebody in. I can't see who it is. It looks like it's Dre. I believe it is. Okay, so let me mark Dre here, and then I'll check and make sure I saw the right person. Okay, let's see if Dre is in here now. Yep, there's Dre. Okay, should have 7 students now. 1, 2, 3, 4, 5, 6, 7, 8. So somebody must have had to leave. Hopefully they will be coming back. Okay, welcome Dre. We're in chapter 3, energy chapter. We're in on page 65, just talking about power. Now, we were talking about the experiment we would have done if we were on campus. You'd have been walking up the stairs. The force that you were overcoming was your weight. The distance was the height of the stairs. Only the height. Doesn't matter about the horizontal displacement, only the height. Because it's the force due to gravity is straight down. You're only interested in the displacement upward, not laterally, but upward. Okay, so you would have measured your weight times the displacement that you had, how high the stairs were, and then you would divide it by how long it took you to walk up the stairs. That would be force in pounds times height in feet. That would be foot-pounds, and then divide that by your time, foot-pounds per second. Okay, now you probably would have then divided by 550 foot-pounds per second, which is 1 horsepower. You would have calculated how many horsepower you had. Not very many, maybe a quarter or something like that. But then you would have run up the stairs safely, not fast as possible, but safely run up the stairs at a good clip, and your weight is still the same, the displacement is still the same, so the work done was the same, but now you did it in a shorter time period because you ran up the stairs rather than walking up the stairs, so therefore your power was greater. And that's why some of you probably would have exceeded 1 horsepower. Usually if I'm doing it, I probably wouldn't, but I have before, but my knees have been giving me problems. I probably wouldn't have gone as fast as I could go. Now they have one little blurb down here talking about your power bill. I don't know if y'all pay your own power bill, or mom or dad does, or someone like that, but guess what? You're not paying for power. You're paying for energy. And if you paid attention to that power bill, your power you used was not watts, but kilowatts, thousands of watts. But if you paid attention to the bill, that's not what you're paying for. You're paying for kilowatt hours, which is power in kilowatts multiplied by time. But look back here again. I can't get it to go backwards. Let me click on this. If you multiply both sides here by time, that gives you kilowatt time hours. That would give you work or energy. That's what you're paying for in your power bill. It's not a power bill, it's an energy bill. That's what you're paying for, kilowatt hours. Okay, now here's the illustration of this. Look at that poor old tired man. It looks like I feel right now. Okay, he's just going to walk slowly up the steps. Okay, his weight, that's the force that he's exerting, times the height. So his weight is his mass times acceleration due to gravity times his height. That gives how much work he did going up the stairs. Okay? Or he drank his energy drink there and feeling much sprier. Same work. Mass times acceleration due to gravity, that's force, times the height, same height. Okay? He did the same amount of work. However, he did it, this was a very slow time, meaning a large time interval. This is a very short time or a fast time interval, and therefore he did more power here than he did there. Okay, that's the difference in power. Now, do you remember a few classes ago, it seems like, I gave the illustration of digging out our patios. Okay, and I was talking about trying to move that big boulder that I found in the middle of the patio when I was digging it out, and how I grunted and pushed and shoved and stuff, but if I didn't move that thing, I was doing no work. Well, let's go back to that situation. Once I got that rock boulder out of the way, and once we made progress there, I worked for about, I'm just going to estimate, about 5 weeks that summer when I was not teaching. I taught for the first 5 weeks, the mini term, and then didn't teach the second 5 weeks. That's when I did most of the digging on our patio. And sure enough, that boulder slowed me down big time, but I worked pretty much 5 weeks. But at the end of those 5 weeks, we're supposed to go back to work. And when we're on the quarter system, we usually started back right around Labor Day, early September. Okay? And it seems like Labor Day may have been on the very first day of the month that year. I don't remember for sure. But I was scheduled to go back to work, but I was only about half through digging that patio. Now, again, that big old boulder in the middle, that slowed me down big time, but I was only about half through. But remember I said I started digging with pick, shovel, and wheelbarrow just because there was no room to get a bobcat in there. Oh, here comes somebody, Tobias. Okay, he must have been the one who had to step out, and now he's back, and I've already got him present, so good. Glad you're back, Tobias. Okay, now, so in about 5 weeks, I dug about half of the patio. But I dug out a big enough area we could get a bobcat in there and do the rest of the digging. Because, guess what? 5 weeks I was off all the time. When the 1st of September came and I was going to have to go back to work, I wasn't going to have that much time to work on it. Only have the weekends, and it would have taken me quite a few weekends to finish the job. So we found someone who hired out a bobcat, brought him in, he came in, and in basically about half of a day, he moved as much soil as I had moved in 5 weeks. Now, that's not quite fair, but let's just use that. The reason I say it's not quite fair, all he did was lift it up and put it on top of the bank. That's all he did with his bobcat. What I did, I filled the wheelbarrow and took it down and filled it in on the terraces I was building with the concrete that we had torn up from the some previous owner had poured a concrete slab on the back part of the property, which did absolutely no good. It was actually damaging trees. So we had it broken up, and I built retaining walls with the concrete chunks, and then filled in the soil behind that. So I was doing a bit more, but let's just count it. We did the same amount of work. So what was the difference between me and the Bobcat? We did the same work. I dug out half the patio in 5 weeks. He dug out half the patio in half a day. Okay, what was the difference there? Same work, shorter time period. He had a lot more power than I did. That was a big old Bobcat. I'm going to guess it was probably 250 horsepower. On a good day, I was considerably less than half a horsepower. So his power was much more than me, so they could do the same work in a very small fraction of the time. I was very slow. I took a lot longer, did the same work, but took a lot longer to do so because my power output was way, way less than his. Okay? Does that make sense? Okay. I can't get my slide to advance. Okay. Now, there is a little blurb on page 65 talking about bookwork. You can read that if you want to. It's a decent little experiment. Okay. And we'll move on over to, page 68. Okay, hold on just a minute. I need a little more energy here. My anemia just really is wearing me down. I'm going to back up at least one slide here. Top of page 68, example 3.3. Now this is where we're talking about the electrical bill, which is the energy bill, not the power bill. I know you're paying Alabama Power or whoever you're paying, but you're paying for energy, not for power. Okay? So here is the problem. If I can find my pen here. There it is. An electric lift can raise a 500 kilogram mass. Okay, they just told us what it is. The mass is 500.0 kilograms. That's the mass. A distance of 10 meters. Now that's pretty good height there. Let me see if I can find my pen. Here it is. The distance that you lifted this was 10.0 meters. Okay, now just to give you a perspective, this wall back here, we've got about 10-foot ceiling in this room, maybe not quite. 10 feet is very close to 3 meters, okay, because a meter is a little bit longer than a yard, and 9 feet would be 3 yards. So since a meter is a little bit further, pretty close to 3 meters would be the height of this wall. Okay, well, we're talking about 10 meters, so that's 3 times the height. So we're talking about the height of a 3-story house or building or something like that. If any of you are familiar with the Bastrop campus, that little part of the building where the library sticks out one end of it, if you come back a little ways, that's 3 stories high. The ground floor is down there where, say, Mr. Holloway's classroom is, and then the next level is where a lot of the English and some math classrooms are on that level, and then the top floor, that would be where your office administration, your accounting, and those kind of classes meet. So 3 stories high, that's about 10 meters. So this lift can pick up 500 kilograms, which is pretty massive, 10 meters. Okay, not just that, in 5 seconds. So if I can find my pen again, Where did you go, pen? There we go. Okay, so your time interval, I like to call it delta t, the book just calls it t. The time interval is 5.0 seconds. Okay, what is the power of the lift? Okay, well, what is power? That's what we're looking for here. What is power? Well, if you remember, power is work divided by time. But we don't have work here. What is work? Work is force times the displacement. And then you divide that by time. We don't have force. Okay? Well, we sort of do. What is force? That's the weight. The weight is your mass times acceleration due to gravity. So this would be mg times d divided by t. So let's plug it in and see what we get. 500 kilograms, 500.0 kilograms, that's your mass, times g, which is the acceleration due to gravity, 9.8 meters per second squared, acceleration units, times your displacement here, 10 meters, okay, and then you divide that by the time it took to lift that, and that was 5.0 seconds. Okay, well, I'll do some of this because it's pretty easy. 5 will go into 500 100 times. Okay, so that gets rid of that. So 100 times 10 would be 1,000. This would be 9,800. What unit would that be? Kilogram meter squared per second squared. Okay, that's joule per second because we already divided this out. So this would be about 9.8 kilowatts. Okay, because a joule per second is a watt. This would be about 9.8 kilowatts. Now, have I got my units right? I mean my significant digits right? Sure, this was 4 significant digits here. If I could find my pen, where is it? Where in the world is my pen here? There it is. Okay, there we go. 4 significant digits there, multiplied by 3 significant digits, that's only 3, divided by 2 significant digits, that gets you down to 2, and 9.8 is 2 significant digits. So about 9.8 kilowatts. Okay, now they do mention something else here. They want to get that not in terms of watts, but in terms of horsepower. Okay, now they did give you some what do you call them, conversions to go from one to another. So let's take a look on the bottom of page 66, left hand column. Okay, now here are some of those conversions. Okay, here is the one they give you here. It takes about 700, I wish I could find my pen, where is it? There it is. 746 watts equals 1 horsepower. Okay, remember, watt is a measure of power. This is joules per second. Horsepower is 550 foot-pounds per second. So these are equivalent units. So if you had here 9.8 kilowatts, okay, now I'm going to change that to watts. And kilo means 1,000, so that would be 9,800 watts. Okay, I'm going to multiply this by converting our units. Remember, we use the train track method. We're trying to get to horsepower. Okay, Well, always notice there's two lines here. One's for numbers, one for units. Always put the units into place. You want the horsepower up here. You want the watts down here. And we just found out that 746 watts, 746 watts makes 1 horsepower. So what do we do with that? We take the numerator here, divide it by the denominator. So let me pull out my handy dandy calculator here, which is my telephone. Whoa, goodness, I almost lost my pen. Okay, and that's an expensive pen. Okay. So it's 9,800. Oh, wait. Okay. I didn't log into my phone, so I was doing something that made no sense whatsoever. Okay. 9,800 watts. 9,800 watts. Divide that by 740. I'm saying 9,800 watts. Divide that by 746. Whoops, didn't take right. 746 watts is 1 horsepower, and that gives you about 13.3 and the 0.1 horsepower. So that 9.8 kilowatts. Where in the world is my pen now? There it is, I think. Right there it is. This is about the same as, I'll put it over here, 13.1 horsepower, approximately. So a horsepower is a little bit smaller unit than a kilowatt, but it's a way bigger unit than a watt. 1 horsepower is 746 watts. 1 kilowatt is 1,000 watts. So you see, a horsepower is a little bit less than a kilowatt, but they are approximately equivalent. Not exact, but approximate. Okay? So that gave us the answer that they got on page 68. Now the difference is they didn't round to 0.1, they just said about 13 horsepower. Okay, and if I could get my pen to show up somewhere here. Where in the world is my pen? Here we go. So let's just wipe out the 0.1. Now it looked like someone was trying to get in the course. Let's see if they are. Nope, it still looks like 8 students here. I believe that's because somebody just came back in. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, we got the right number. Okay. So I hope nobody new is waiting out there. Yeah, looks like we got everybody. All right, any question on power and how we go back and forth with it? Okay, now let's clear my scratch here, and I can't see it come up here. So let me click on this. There it is. Okay, let's erase all that ink. Now, a 150-pound person, okay, let's start writing this down. A 150-pound person, and they call it exactly that. This is a measure of weight, force due to gravity, okay? Runs up a 15-foot stairway, so there's your displacement, 15 feet, and that is your distance that you ran, upward, not laterally, but upward. In 10 seconds, that's your time. 10 seconds is your time interval, and they call that 10.0 seconds, okay? Don't know why they had 2 significant digits for pounds, 2 significant digits for feet, but 3 significant digits for seconds. What is the horsepower rating of that person? Well, we have to figure out horsepower then, okay? and I wish I could get the pin to show up. Oh, there it is. Okay, so what we're looking for is power, and power is work times displacement. No, sorry about that. Yuck, I'm getting my numbers all crossed up. There we go. Yuck. This is such a pain in the neck. Okay. All right, let's start that over. Okay, what is power? Power is foot-pounds per second. And that's what we're dealing with, foot-pounds. So this is work divided by time. Okay? Now, we've got what work is. Like I just said, if I could get my units to come back. There they are. Work is force times displacement divided by time. That's what power is. And this is, your force is your weight, 150 pounds times 15 feet divided by 10 seconds. Okay? Now I'm doing this in my head, so correct me if I'm wrong. 15 times 150, I'm pretty sure is wherever my pen is. This pen just keeps disappearing on me. Where in the world is my pen? I can't find it. There it is. Okay. I think that's 225 or 2250. That would be foot-pounds divided by 10.0 seconds. Okay, this 0 will wipe out that 0. So that is a power unit of 225 foot-pounds per second. I don't know where I can write that. There we go, somewhere here. So 225 foot-pounds per second. That was your power. Okay, but that's not measured in horsepower. That's just power, 225 foot-pounds per second. But we know, if I could find my pen again, it just keeps leaving. There it is. Okay, we're going to multiply that by blank blank equal, and we want this in blank horsepower. Okay, what are we going to do? We're going to put horsepower on top, and how many foot-pounds? This is such a pain in the neck. Foot-pounds, again, I don't know if you can see it when it happened. Foot-pounds per second. Okay, that's hard to read because of their stupid little block there. Okay, well, how many? Here are the foot-pounds per second. If I could get my pen to show up. Where in the world is the pen? Okay. Okay, there it is. The foot-pounds per second here cancels out the foot-pounds per second down here. And what was that? 1 horsepower is 550 foot-pounds per second. So since the foot-pounds per second canceled out, we take the numerators, 225, divide it by 550. So now it's time for my calculator. Got to log in again. Calculator mode. 225 divided by 550 equal, that looks about to be 0.41 horsepower. Okay, is that enough digits? Here we have 3 digits here, 2 digits here, 3 digit here. This may only be 2, so it looks like we can only get 2 digits out of that, so it looks like 0.41 horsepower will be about it. Okay. Now that person isn't moving all that swiftly. Just about everyone that's done this exercise before. Now, admittedly, what did I say that was? 0.41. Come on, where are you, pen? This pen just disappears. There it is down here. So let's go up here. 0.41 horsepower. That person isn't moving all that fast. 10 seconds to go 15 feet up, that's not moving very fast at all. Said he was running, don't believe he was running very hard. That's only 0.41 horsepower. Most of the time, most people can make that when we did it on campus, and walking it was just a little, maybe a few seconds more than 10 seconds. So they weren't running very fast at all. Of course, we were only going up 12 feet. They were going up 15. So, okay. Let's see what they got. 0.41 horsepower. Good for them. Okay. Now I think we're ready for 3.2. Motion, position, and energy. I'm going to have to take a quick time out again and get me some more caffeine and sugar. I'm sorry. I'm just so, well, end of the week too, I'm just out of energy. All right. Now, motion, position, and energy. How are we doing on time? 4:26. We got a little over an hour to go. Okay. Work and energy are related. Okay. Big time they're related. They have the same units. Joules in the SI system, foot-pounds in the US customary system. They are related. Okay. Energy has been said to be the ability to do work. You have enough energy to run up those stairs. That's the work you did was running up the stairs. The energy was what you expended to run up the stairs. Okay? On the other hand, work is the process of changing your energy level. When you're at the bottom of the stairs, you're at one energy level. Top of the stairs, you're at a higher energy level. Work is the process of changing your energy level. You had to do work to get from the lower floor to the upper floor. Process of changing energy levels. Okay? The next thing we're going to talk about would then be the relationship between motion, position, and energy. And that relationship between work and energy is associated with position. Okay? Now, I usually would give this example in a class. If I were to hold the book over someone's foot, who is it? Jacob, sitting near the front of the classroom there, and I hold the book over his foot and release it. Okay? If he moves fast enough, he'll probably move his foot out of the way. But if I were to hold it just above his foot and release it, he probably isn't going to object too much, because guess what? The book has more energy when I hold it up here than it did when I held it just over his foot, because there is a relationship between the work or the energy that that book had and its position. Okay? If I were to hold that book way up here and release it, it's going to hurt when it hit the ground. If I hold it way down here just above his foot and release it, I hardly notice it, because there's a relationship between work and the energy associated with position. Okay, alrighty. Sorry about that. Not really, but okay. Now, there's also a relationship between work and the energy of motion. Okay? Now, let's picture this one. I'm standing in the front of the classroom, and I have a ping pong ball. And I rear back and I throw that ball as hard as I can toward who's sitting in the back of the room now. Maybe that's Thomas back there. Throw it as hard as I can toward Thomas because it looked like he may be fading out. I want to wake him up. Hey, he's not even going to notice it, because the energy of motion, that ping pong ball just doesn't have that much motion. It's such a small ping pong ball. Now, what if I had a bowling ball and threw at him? No, I'd get in big trouble for that, because that could do some serious damage. So the energy of motion, there's also a relationship between work and the energy of motion, between work and the energy of position, and work and the energy of motion. Okay. Now, the first of those, the position energy, is called potential energy, the energy associated with position. Okay. Now, a lot of times that's how far above, like when I was lifting the book up here and the foot was down there, that is gravitational potential energy. What you're measuring is the height, or the delta height, and you need some sort of reference on it. Okay, so let's picture again, we're in the classroom. Okay, now I'm up on the second floor is where my classroom was. If I were holding the book above the desktop here, and that may hold it about a foot over the desktop. If the desktop is as low as that book is going to go, that would be 1 foot would be my reference height. The desktop would be my reference height. However, if I pulled the book over and held it over the floor, oh, here comes Gerald. Let me get Gerald here before it fades out. Okay, and get Gerald present here. All right. All right, that should get us up to 12 students. Let's see if that's right. No, we only got 9 students here. Okay, I'm sorry, I missed that. 9 students, you're right, 9 students. Okay. Now, what we refer to that as a reference height. If the reference height is the floor rather than the desktop, then that's your reference height. Now, what we call that is sometimes the zero reference level. In other words, typically that's as far down as the book can go in that particular problem. If as far as it can go is the desktop, that's your zero reference level. If as far down as it can go is the floor, that's the reference level. However, when I went over to the window and dropped it out onto the ground becomes my reference level. So you just have to decide what your reference height is, where you're measuring your H, from the low as it could go up to the height that you're dealing with. Okay, that's called the reference height, also called the zero reference level. All right, now that's not the only form of potential energy. Spring potential energy, which is also called elastic potential energy, that is a function of position too. If you compress a spring, you know it's pushing back at you, so you're adding energy to the spring. If you stretch the spring, it's pulling back in toward the middle. That's also creating potential energy. Another, electric charges. You could have a positive charge here and a negative charge here. They're going to try to attract to each other. To keep them apart, you have to be expressing potential energy because of their distance between each other. However, if this was positive and that was positive, they're pushing each other apart. You would have to push them back together, do work on them to keep them happy. So work can change your potential energy. If I lift the book over the desktop, I'm doing work on the book, increasing its potential energy. Because it was down here, I moved it up there, I've increased the potential energy because of that height above the reference level, the desktop, got increased. Okay? Kinetic energy can also change into potential energy. How is that? Let's throw a ball up into the air. Okay? If you throw the ball up into the air, you're giving energy to the ball, throwing it up there. That's kinetic energy, by the way. And when you do that, the ball leaves your hand and starts going up. But as it goes up, it loses speed because it's expending some of that energy you gave it until it reaches its maximum height where it's at zero speed and then starts falling down again, picking speed back up. So that kinetic energy with which you threw the ball upward, it changes the potential energy. The higher it goes, the more potential energy it has until it stops, and then it starts losing potential energy as it comes back down, but gaining kinetic energy because it starts speeding up again. So kinetic energy can also change into potential energy and potential energy into kinetic energy. Okay, potential energy is the energy associated with motion. Kinetic energy is the energy associated with speed or velocity. We'll get to that in just a minute. I can't get my slide to progress. Here it goes. So here we have a building, looks like about a 4-story building. Don't have one of those on Bessemer campus anyway, do on the Birmingham campus. And you hold the book outside the window up on the 4th floor. What is the potential? Well, actually, we keep it inside the building, and its height above the floor, that's its reference height. That's as low as the book can go in that room. Okay, so there's your reference height. Okay, however, if you hold it out the window, then it could go all the way down to here. Okay, well then you either change your reference height to down here, and that's a greater height here, or you have a negative potential energy down here because you had a positive potential energy here, mgh. Mg is the weight times the height. That's your potential energy, mgh. They gave it to you, but I forgot to mention it to you. That's your potential energy, mgh. Gravitational potential energy, that's what the G's in there for. However, if you hold it out the window and you can go this far, now you have negative potential energy because your height now that it falls is a negative height from where it started, which is the floor of the 4th floor down to ground level. So that would be minus mgh. That would be a negative potential energy. So potential energy can either be positive or negative. Most of the time we try to keep it positive, but occasionally it'll sneak a negative into you. Okay. Now before we go to kinetic energy, there are a couple of examples there too. So this is on page 69, so let's do this one. All right, we'll do it here. Let me get my pen and pad. Okay, this is on page 69, example 3.5. What is the potential energy? Now, when I talk about potential energy, I use a symbol. Okay, I usually do GPE, gravitational potential energy. The book quite often will just say PE, but you're not making a distinction between elastic potential energy, spring potential energy, electrical potential energy. They just say PE. I like to say GPE, meaning gravitational potential energy. So what is the potential energy or the gravitational potential energy of a 2.14 kilogram book? Now that's about the mass of your book. So this is what we're looking for. If I could get the pen to show up here. There we go. This is what we're looking for. And what we have is a 2.14 kilogram book. So that's a measure of mass. The mass of the book is 2.14 kilograms. Remember, kilogram measures mass, not weight, mass. That is on a bookshelf 1 meter above the floor. Well, there's the height. That's the one we're using here. The height is 1.0 meters above the floor. So obviously we're taking the floor as our zero reference level because the height or the delta H is 1 meter. Well, what is GPE? Where is my pen go? I can't find my pen. There it is, maybe. All right, so what is it? There it is. The GPE is mgh. So your M here is 2.14 kilograms. That's the M. The G, of course, is 9.8 because we're in SI units, meters per second squared, and your height is just 1.0 meters. Okay, that's not going to change a lot. So what are your units here? Okay, I'm going to have to get my calculator to do this, but the units are kilogram meter squared per second squared, which by the way is a joule. So our unit is joule, kilogram meter squared per second squared. Let me get my phone to do the calculation here because I can't do that in my head, or at least I don't want to. Okay, so it's 2.14 times 9.8, and the next part is easy, times 1, and that's equal to 20.972 joules. Well, we only have at best two significant digits, so let's make that 21 joules, approximately 21 joules. So I will write that as, if I can get my pen now, there it is. This is approximately 21 joules. Okay, let's see how the book did. 21 joules, good for that. Okay, example 3.6, right under that one, it says how much work can a 5 kilogram mass, so this is going to be a completely different problem. So let's clear our screen here. Okay, now it says how much work, so here we're measuring work. If I could find my pen now, where is it? There it is. So now we're looking for work. That's what we're looking for. How much work can a 5 kilogram mass, so there's the mass, is equal to 5.00 kilograms, do if it is 5 meters above the ground. Okay, that's pretty high. So that's your displacement is 5.00 meters above the ground. Alright, so how much work can it do? Well, work is how much potential energy did it have? Well, the potential energy was, if I can find my unit, here we go. Okay, so GPE is equal to mgh. We know the mass of 5.00 meters, no, kilograms, times G, 9.8 meters per second squared, times height, 5.00 meters. Okay, so that's 25 times 9.8. Again, I can't do that in my head. Can come close maybe. 25 times 9.8. 9.8 equal about 245 kilogram meter squared per second squared. That would be joules. Okay, so that's approximately 245 joules. Okay, 245 joules. But we only have 3 significant digits here. If I could find my pen, there it is. 3 significant digits here, but here we only have 2. So they take this, oh, and this is joule, and round that to 2 significant digits. Count over 1, 2, look to the right, that's 5 or more, so they call this 250 joules. Okay, now that almost seems like we didn't use any energy at all there, but we did. gravitational potential energy. Okay? And that's what they get at 250 joules. Now, before we move on to elsewhere, there is a little blurb, work and power. Okay? And this is the experiment that we would be doing in class today. We're not, but this is how you can read it. If you want to play around with this at home, you certainly can. Your walking power versus your running power. The difference is not how much work you do. If you go up the same flight of stairs, you've done the same work. What makes the difference is how much time it took you. The smaller length of time, the greater the power. The longer the length of time, the less the power. Okay? Just like me and the Bobcat. Okay. So let's move on to kinetic energy. Kinetic energy is the energy associated with motion, not position. Position is potential energy. Kinetic energy is energy associated with motion. Now, what is required for motion to be happening? You have to be changing position over a time interval. That means you have to have a velocity. So it's a result from either work or change of potential energy, either one of them. Okay? Let's say that you're holding a baseball and you're going to throw the baseball. You are giving the baseball more kinetic energy because you're increasing its speed from rest in your hand to something greater than rest when you throw it. Okay? That's result from work. Or if you throw that ball straight upward, you're doing work to the thing, but now you're changing its potential energy, so the kinetic energy is actually decreasing as it goes down. Now, what they didn't show you, or maybe they will here, is what's the formula. There's the formula. Kinetic energy is the energy of motion, so if you have motion, you've got to have velocity. So the formula is 1/2 mv squared. And remember, from way back, I said, about 2 weeks ago, I said that most of the time when your variable is raised to the second power, you'll have a 2 in the denominator. And in this case, you do 1/2 mass times velocity squared. Okay? Notice the speed is squared. In potential energy, GPE is mgh. Everything's to the first power. Kinetic energy, 1/2 mv squared. That means when you double a velocity, you quadruple the amount of kinetic energy. Triple the velocity, 9 times the kinetic energy. So the kinetic energy increases big time as you increase speed. Okay? Now, that's all they have for kinetic energy, one slide. They do show a couple of examples. Let's go back and do the examples. Okay? We'll be using that formula, but let me have some gray space to write it on. Okay? Goodness gracious, I'm tired. Oh, and by the way, let's look at that. Let's go back to that one. Okay? All right. Let's look at the units for kinetic energy. Okay? 1/2 is just a number. It has no units associated with it. Mass is measured in kilograms. Velocity is measured in meters per second, but you're squaring that. So what's your unit? Kilogram, because 1/2 has no units. Meter squared per second squared. If you remember back what your potential energy was, I like to call it GPE. That was mgh, which is mass is measured in kilograms. G is measured in meters per second squared. It's an acceleration due to gravity. And your height is measured in meters. Okay? Multiply those together. What do you get? Kilogram meter squared per second squared. Same units. Kilogram meter square per second square, kilogram meter square per second square. When you're measuring work, work is force times the displacement. Force is in newtons, which is kilogram meter per second squared, times the displacement meters, kilogram meter square per second squared. All of them have the same units. Joules, foot-pounds, whatever, all of them have the same units. Okay, now, that being said, let's go back and, all right, I'm going to back up or go forward. No, back up one slide here. Okay, sorry folks, I am losing it so fast. It has to be a Thursday, doesn't it? All right, I hope I can make it out. All right, got a little less than an hour to go of class, and then we'll hit toward lab. Here's example 3.7. A 7 kilogram bowling ball. What's that a measure of? That's the mass of the ball. Mass of the bowling ball is 7.00 kilograms. Pretty massive. Is moving in a bowling lane with a velocity, so the velocity of the bowling ball is equal to 5.00 meters per second. Good unit for velocity, speed. What is the kinetic energy of the ball? So we're looking for kinetic energy. That's the unknown here. What's the formula for kinetic energy? We just had it. 1/2 the mass times velocity squared, which would be 1/2 the mass, 7.00 kilograms, that's your mass, times velocity squared, that's 5.00, but that would be meters per second, but you're squaring that. Okay, now nothing's going to cancel out very easily, so this would be 1/2 of 7. Let me just go on and do that. That's 3.50 kilograms. Half of 7 is 3.5. Okay, times, square the number. 5 times 5 is 25.0, but square the units as well. Meter squared per second squared. Okay, now it's time for my calculator. Goodness, I'm ever tired. Oh man. Goodness gracious. I'm just exhausted. Okay, 3.5 times 25 equal, I get 87.5. Where in the world is my pen? There it is. Approximately 87.5 kilogram meter squared per second squared. That would be a joule. So 87.5 joules. And that's what they got. Good for them. Okay. Man. Okay. Let's go down to 3.8. Okay, I believe I'm going to clear my screen here and use the same slide. So erase all the ink from that. All right, now we have a 100 kilogram football player. Just to give you an idea, that's about 220 pounds. So that's a pretty substantial football player. But the kilogram isn't measuring weight, that's measuring mass. So the mass of this football player is 100 kilograms. Okay, that's the mass of the football player. He's moving with a velocity, so the velocity of that football player is 6 meters per second. Okay, if I could find my pen, there it is. 6.0 meters per second. Why they have forcing of it there and only 2 here, I don't know. Okay, he tackles a stationary quarterback. Ooh, big bang here. Hopefully he doesn't target him, but tackles a stationary quarterback. How much work was done on the quarterback? Okay, so work is your change of kinetic energy. So he went from 6 meters per second to 0 meters per second because he crashed him into the ground. So the change of his kinetic energy, that would be the delta KE, would be 1/2 the mass times the velocity squared. Okay, velocity of the football player. I can't think of my terms here. Football player squared. 1/2 mv squared. That's how he changed his potential kinetic energy. So this would be 1/2. Where in the world did the pen go? There it is. 1/2. The mass was 100 kilograms times 6 squared, 6.0 meters per second squared, and this would be 1/2 of 100 would be 50.0. Okay, that's kilograms times 6 squared is 36 point, well, let's just call it 36 meters squared per second squared, because you square the units as well. And what does this come to? Five times 6 would be 30, and 5 times 30 would be 150. 150 and 30 would be 180, I think. I'm doing that in my head. So this, I think, is, goodness gracious, where does the pen go? There, we got it. So that, I think, is approximately 180 kilogram meter squared per second squared, which is about, I left off a digit there. Okay, 36 times 50. The 0, 1 0 goes down. 5 times 6 is 30. There's the other 0. And 5 times 3 is 15 with that other unit 1. Unit 3, that would be 1800 kilogram meter per second squared, which would be approximately 1800 joules. Kilogram meter square per second square would be joules, and if you wanted a smaller number, bigger unit, that would be 1.8, approximately 1.8 megajoules. Kilojoules, sorry, kilojoules. Goodness, I'm losing it fast. 1.8 kilojoules or 1800 joules. They put a comma here, it doesn't matter. Okay, goodness gracious, folks, I'm so sorry. Let me drink some water first. And then maybe some more caffeine. I'm sorry. Okay, so that was example 3.8. 1800 joules or 1.8 kilojoules. Poor quarterback. Okay, he took it on the chin. All right, let's move on to energy flow. This is section 3.3. Okay, got about 45 minutes here. Let's see what we can do. Energy can do work in many ways. Work against inertia. And it seems like one of the pictures they have here is pushing on a car. The car wants to remain right where it is. That's its inertia. Okay? But when you push on it, you give it some velocity and you move it. So that's work against inertia. Or, let's say you're a catcher on the baseball team and that pitcher throws a fastball right down the pie catcher. You're having to work against the inertia of that ball coming in to bring it to a stop. That's also work against inertia. Okay? Energy is required to do work against inertia. Work against gravity. Lifting something off the floor. Gravity's trying to hold it on the floor. You're doing work against that gravity. That gives you energy is work against gravity. Work against friction. You're trying to push this crate across the floor. When you're doing that, the floor and the crate have friction between them. You're doing work against that friction. Now, they give one example of a work against shape. I'm going to give you another one. When I was in Nebraska working on a graduate program, a group of us had a volleyball team, a co-ed volleyball team together. Okay? And it was fun. And it was co-ed, so we had this one really tall gal who had played in high school, and she had with her a good friend of hers, a gal who was a great setter. The tall gal could really spike that thing, and the setter could really set it up for her really nicely to do that. So they were the stars of our team. We went over to play our match one evening, and it just happened to be this team we were playing against had a really tall gal who had not just played in high school, she had played at one of the elite high schools in the state. And not only that, she had her setter with her on the team as well. And boy, that gal could set them up just perfectly for her. So we went, whoops, okay, our strength, they've matched with their strength and maybe even done a little bit better. Well, when you play volleyball, you know, each team circulates in the opposite direction. So after a while, you know you're going to be directly across from any other person on that team, the other team. And when it got to be my turn to be right across the net from this really powerful spiker, and we were watching her in the warm-up, she could really wham that ball. I knew my only chance was to get up, make as big a surface area as I could to try to knock the ball back across the net, because I knew when that gal set it up for her, it was coming and coming fast. So sure enough, we served to them or whatever. They got it to the setter set it up perfectly. I went up in the air trying to block it best I could. That ball came down not anywhere near my hands or arms. It came down flat on my face. Now, I don't know if you've ever played volleyball. Okay, a volleyball isn't as hard as a baseball or a golf ball or something like that, but it's still pumped up pretty hard. About the same, pressure as a basketball. They're really pretty hard, okay? That volleyball came down at such an enormous rate of speed, I felt it touch both ears at the same time. My face did work on that, the shape of that volleyball. All I saw was Wilson, not really, I just made that part up. But anyway, I did work against the shape. Now the one they show is work against the spring. Yes, same deal. You're doing work against the shape. Or against a combination of all of the above and maybe other ones as well. So here are those examples. There's work against inertia, guy pushing on the old Volkswagen Beetle. Okay, his force is in this direction, the displacement's in that direction. He's working against inertia. Inertia is trying to hold it back. He's working against that, pushing it forward. Okay, doing work against inertia. This is work against gravity. Lifting that heavy box off the floor, the force is upward, the displacement's upward, doing work against gravity, which is trying to hold the box downward. Work against gravity. Work against friction. There the gal is pushing that filing cabinet across the floor. There's friction trying to restrict her motion. She's pushing with a force this way, giving a distance that way. She's doing work against friction. Okay? And this is a spring pushing against to compress the spring, or a volleyball. Okay, the force is in this direction, the displacement's in that direction, the shape of the spring is being compressed, which means it's pushing back at you. You're doing work against its shape. Okay, now those were the first part of energy flows. The second part of this is energy forms. Okay, now we've already mentioned several of these forms. We've mentioned work. We've mentioned earlier, we even talked about mass being a form of energy. We talked about the energy of motion, kinetic energy, the energy of position. That's potential energy. Well, here's another one. Mechanical energy is the energy of kinetic plus potential energy. Okay? Another lab we would have done if we were on campus was going to measure the mechanical energy of an object. We'll be doing some of that in today's lab. Okay? That's what mechanical energy is your kinetic energy plus your potential energy. The energy of motion plus the energy of position. Now, when we get to chapter 6, we'll talk about electrical energy. I'm not going to do too much with it now, but we talked about it a little bit before. If you have charges, electrical charges can either be positive or negative, and depending on the sign, they're either going to be attractive forces or repulsive. The work is dealing with that. You also have current, and we'll talk about the energy of currents as well. Going to deal with that later. Chemical energy. That again is mostly a potential energy, the energy involved in chemical reactions. Okay? I've been sipping on a Coke. Why? Because that has sugar in it and I needed some energy. Sugar is stored chemical energy. Where does it come from? Those little green leaves out there on the trees. Now some of them are turning brown or yellow or gold or whatever color, but that's where the energy came from. Those little green leaves have chlorophyll in them, and when the sunlight, which is a form of energy, hits that chlorophyll, it increases and breaks down carbon dioxide, which the leaves suck in out of the air, and also water, which the tree pulls up out of the ground. Okay? Carbon dioxide plus water combined chemically forms a sugar. So CO2, carbon dioxide, plus H2O, if you have enough of them in there, they form let me get it right. H12C6O12. I think I've got that right. Okay? That forms a sugar. Okay? That's stored chemical energy. Then when it gets in your body, your metabolism breaks that apart, and the energy that was stored in building those sugar molecules now is released, which gives you temperature. Okay? That's why you have a temperature of 98.6 or somewhere there around. Why? Because you're converting chemical energy into heat energy. It also gives you energy to lift those boxes, to push on the cars, to reshape that volleyball or spring or whatever. That's chemical energy. Now we'll talk just a little bit about that in chapter 8, but that's right at the end of the term. Okay? Radiant energy, that's the energy due to electromagnetic energy. Now here we talked about electric energy, which is charges and currents. Electromagnetic energy is basically fields, okay? Electrical fields and magnetic fields, how they interact with each other, and they haul around what they call radiant or electromagnetic energy, and that's one form is visible light. That's the light coming from the sun that those little green leaves transfer into chemical energy when they make the sugars. One of the trees out there in our yard is, two of them in fact, are pecan trees. They make fats, the oils in the pecan. We have other trees. There's a walnut tree back there. That makes a fat. We have several oak trees. They make acorns, which again, largely oils and fats, okay? So all those energies are being formed from sunlight energy, reformed into other forms of energy. That radiant energy is your sunlight, okay? Now, there's also nuclear energy. That's one of the few types of energy. Okay, let me back off a moment. Where does the sun get its energy? From nuclear energy. The sun is one huge, constantly operating nuclear energy plant. The sun is sending out radiant energy coming from nuclear energy. We call it fusion energy, where two hydrogens are fusing together to form a helium. That gives off enormous amounts of energy. And some of that radiant energy that goes out into space, and much of that is really deadly high energy radiation, like gamma rays, X-rays, all sorts of rays. Fortunately, our atmosphere blocks most of those rays and only allows that visible light to come through. That's a very small part of the full spectrum given off by the sun, but it's just what we need. Any more than that, we're going to be dead. Okay, we're going to be toast, because that radiation can destroy tissues. In fact, those people who are sun worshipers, they get out there and lie around in the sun, they are killing tissue. Okay, that's what they're doing. Their body is trying to repel the damage being done by that sun, that visible light, electromagnetic energy, and their bodies are trying to produce enough keratin to keep that from damaging tissue. Okay, a lot of times it doesn't, and over the years people are going to get things like skin cancers, different types of skin cancers, cataracts. I've had both cataracts removed, one from each eye. It damages tissue. That radiant energy coming from the sun. The light energy doesn't do that much damage. It's that ultraviolet that does do the damage. Well, that's coming from nuclear energy on the sun. Energy involved with the nucleus and nuclear reactions. That's nuclear energy. Now, some of our power plants are nuclear power plants. They're using the nuclear energy of, now there is fission rather than fusion, okay? And it's, don't know how to say this exactly. We're going to talk about it later. In some senses, it's a cleaner energy because it's not producing any smog or pollution or something like that. But on the other hand, the waste products are really dangerous, okay? So even though it's a clean energy, it does produce some pretty nasty waste products, okay? But that's nuclear energy. Now, nuclear energy is where the sun gets its strength, but the nuclear energy we produce electricity on the earth, that's coming from different nuclear source. Now, that was page 71 on to 72 on to 73, and we're getting to energy conversion here. Okay, we've got about half an hour to go. Let's just do a little bit of showing you some of the things that the slideshow isn't showing. Here is a boat. I bet you that has a motor that is fueled with petroleum, okay? And that boat, as it turns the screw, the energy of the petroleum is used to turn the propeller, pushes against the water, that pushes the boat forward, that gets us your speed. That stored potential energy of the petroleum, chemical energy, that is converted into mechanical energy. Okay, that's the energy of motion, kinetic energy of the boat. Also, is pushing against water. The water also gains some potential kinetic energy. Here we have the wood from those trees. Okay, those trees produced a complex carbohydrate called cellulose. You can burn that cellulose and produce heat. You can cook food with it. You can do whatever. Okay, here is a picture of a coal pile, I believe you would call it. If you've ever been out what's the name of that? Birmingport Road. It's, I think, Highway 369 or so. If you've ever gone out there, it's a long, lonely drive, but go out there, you hit a place called Birmingport, and you'll see mounds and mounds and mounds of coal. Now, I can't tell you exactly where that coal's coming from. We do a lot of coal mining in Alabama, but our coal is pretty dirty. So some of that coal may be stuff that's mined here, but they send it down the, I think that may be the Warrior River, I'm not sure. Send it down the river and send it down to South America, Central America, somewhere like that, and they burn our nasty coal, okay? They pollute the same air that we breathe too, by the way. Other of that coal comes from, say, the Midwest or far west, like Wyoming. They have pretty clean coal there. So we bring coal in and we burn that at our power plants. And if you happen to be driving out that new Interstate 22 that goes to Memphis, you'll see some of those great big old stacks over there where the cleaner coal is being burned to produce our electricity. So here we're talking about one energy form being converted into another. Okay, that picture illustrates the coal. Stored chemical energy that was stored millennia ago, long times ago. Okay, now here's something a bit more current. These are solar cells. Okay, that's taking sunlight, direct sunlight, and converting it into electrical energy. So there's another form of energy conversion. Early in the chapter we saw pictures of wind turbines. That's taking the energy, the kinetic energy of the wind, converting that into very clean electrical energy there. We've got to be increasing those clean sources at the expense of the dirty sources. So what we're talking about here are energy conversions. But before we get to that one, let's do this one other figure here, and this is the electromagnetic spectrum. See, at the top they give you gamma rays. Those gamma rays are incredibly powerful, destructive waves. If we didn't have our atmosphere on us, we would be toast. Those kill tissue. Because we have such a wonderful atmosphere around us, it blocks most of that deadly waves. Below that you see X-rays. X-rays are also deadly. You might say, wait a minute, don't we have X-rays when we break a bone or fitting shoes or do different things like that? Yes, we do, but it's very low power X-rays. And it only hits for a very short period of time. Your body can overcome that. But if you've ever noticed, the X-ray technicians, before they ever turn on the machine, think of your dentist office. They take X-rays of your mouth, right? Before they ever turn on that machine, they get behind a really thick leaded glass and get into a room by themselves, and then they turn on the machine. Just a little bit of that goes to hit your teeth, so they take a picture of that. If they were to stay out there with you, time after time after time, they would get too much radiation and they would have to quit for a month or for some length of time and not do any more X-rays. That's why they get behind that thick wall which has lead in the wall, preventing that. So those are the X-rays. They are deadly. Above that is the ultraviolet radiation, below the x-rays are ultraviolet radiation. They also damage tissue. They cause skin cancers, they cause cataracts, they cause wrinkling of your skin. Fortunately, our atmosphere blocks most of those, but not all of them. Now, we put on sunblock to block most of the rest of them. That's called the UV protection, ultraviolet protection. Then we have that narrow little band of the colored spectrum. And that starts at the bottom with red, orange, yellow, green, blue, indigo, whatever that is, and violet. Roy G. Biv. That's their visible light spectrum. That's basically what our atmosphere allows through. That's what the trees use to convert carbon dioxide and water into simple sugars and other oils and things like that. Beneath that, on the lower side of the red, you have infrared. That's your heat energy. Okay, that heat energy is what happens to that light when it comes through our atmosphere. It lengthens the wavelength, which lowers its energy. Now it doesn't have enough energy to get back out of our atmosphere, and that's why we have things like global warming. We're so far from the sun, we would be too cold if it weren't for the fact that that visible light that comes in gets expanded a little bit and becomes infrared energy, which increases heat. Have you ever heard of a greenhouse and the greenhouse effect, greenhouse gases? We have a little one behind our garage over there. You can't see it from here, but pretty close to seeing that. And what we do in the wintertime, we put our plants in that, and as long as it doesn't get too cold at night, that traps a little bit of heat from the sun. So in the daytime especially, traps the heat from the sun and keeps the plants inside the greenhouse warmer because of that greenhouse effect. It's the same thing that happens to your cars. Okay, I bet you every one of you have gone out in the summertime when you parked your car out in the parking lot, no trees or anything around, park the car out there, gone out there and get into your car and it is burning up. The reason is the glass has greenhouse characteristics. That's why they call it greenhouse. The energy coming in gets lengthened in its wavelength, which reduces its frequency, which changes it from visible light, white light, into infrared. The infrared cannot escape, and so the inside of your car becomes incredibly hot. Now, that's also what makes it very dangerous for people like in daycares or people who own pets to leave their child or pets inside a car closed up in the summertime. It can get so incredibly hot in there, the child or the pet could suffer enormously, even to the point of death. You don't want that to happen. Okay, be very careful that you don't leave a child or a pet in a car in the summertime. Now in the wintertime, if it's a nice bright sunny day, even though it's 40 degrees outside and feels really cold, that car feels nice and toasty when you get in. Why? Because of the same process. Even though it's cold outside, the white light, the energy of the light comes in, lengthens in wavelength, which reduces its frequency, which drops down to infrared radiation. It cannot escape. It warms up the interior of the car. All right. Those are all situations for for energy conversion. Let's go down a little bit further and you see microwaves, FM and TV, electromagnetic radiation. Somewhere down there you get AM radiation, and then you get long length radio waves. Okay, those are all on what they call the electromagnetic spectrum. The ones below visible light don't usually hurt us. Okay, the ones above the visible light can do more and more damage the higher you go. All right, so let's talk about this energy conversion. Those are the pictures. Let's talk about it. Any form of energy can be converted into another form. Now that's a pretty general statement, and most of the time that is pretty much true. There are a few examples that's hard to convert, so we'll talk about those in a minute. The energy flows from one form to another in natural processes, usually flowing from high energy level to low energy level. That's your natural process. Very seldom you go from low energy to high energy. That's going against nature. Okay? Now, one example of that is a pendulum. Now, one place that you probably recognize a pendulum in a grandfather clock. It goes back and forth and back and forth. Let's see if they show it here. Well, before we get to the pendulum, here's one. Here's the bowler. He lifts that bowling ball, increasing its potential energy because that's the energy of position, increasing that, and then as he moves his arm down, he's both increasing the velocity of that bowling ball, which is increasing its kinetic energy. He's also lowering the bowling ball, which converts the potential energy up here to kinetic energy down here. So when he finally releases, the ball has almost no potential energy, lots of kinetic energy, the energy of motion. Up here, it's all energy of position. Okay? Now, that bowling ball rolls down the alley here. If it's meat behind it, it probably rolls into the gutter. But if you're a good bowler, stays on the alley, hits the pins, knocks them all over the place, doing work on the pins, increasing their kinetic energy, which was zero to begin with, and losing the kinetic energy the ball had. Some of it hits the back of the place there and comes to a stop. Okay? But there you have potential energy becoming kinetic energy hitting other objects, giving more kinetic energy, whereas they didn't have kinetic energy before. Now they do. That slows down the bowling ball, and ultimately it stops. Okay? So that's an example of energy conversion. Potential to kinetic to different forms of kinetic. Okay? That's one. Here's a pendulum. Okay. When the pendulum is at rest, hanging there, not doing a thing, that is its zero potential energy, because the delta H here is zero. The height is at the zero reference level. There is no potential energy. However, if you're trying to start that grandfather clock going, you raise that pendulum up to whatever its maximum height is. Now it has 100% potential energy, energy of position, zero kinetic energy. Why? Because you raise it up there and hold it. No velocity, no kinetic energy. Okay. When you release it from rest, release it from your hand, now it starts picking up speed, which gives it kinetic energy. As it's falling, it loses its potential energy till it gets back down here. No potential energy, 100% of kinetic energy. So whatever potential energy it had here, it has the same amount of kinetic energy here. Now halfway up between the maximum position, H, and the minimum position, H equals 0, it's 50% potential, 50% kinetic. It has some speed here, no speed here, maximum speed here. Okay? So that is, but the mechanical energy is constant. The mechanical energy is the sum of potential plus kinetic, potential plus kinetic, potential plus kinetic. The sum has to be equal to mechanical energy. We'll be doing that in today's lab. Speaking of which, we got about 15 minutes till we get there. Okay? Now, all right, here is your equation. Mechanical energy, I call this ME, of the pendulum, is a fixed constant amount. It's the sum of kinetic and potential energy. I like to call this GPE for gravitational potential. Okay, the sum of those two is your mechanical energy. I call it capital ME. Okay, now here's interesting little formula here. Okay, let's go back to, oh no, this slide right here is fine. Okay, let me get my pen and pad here. Okay, like we said here, all the energy of this pendulum, if I can get my pen to show up, I know it's somewhere there. I can't see it anywhere. Oh, there it is. Okay, here. 100% of your energy here is potential energy. That's mgh, where h is the height, m is the mass, and g is the acceleration due to gravity. Down here at the bottom, the height is 0. So 100% of your energy here is kinetic energy because you have 0 potential energy. Well, your kinetic energy is 1/2 mv squared. So since all this is kinetic potential energy up here, it's all kinetic energy here. The mechanical energy is 0 plus 100%. Your kinetic energy, your mechanical energy here is 0 plus 100%. So these are the same. So your mgh is equal to your 1/2 mv squared. 1/2 mv squared at the bottom equals mgh at the top. Now the first thing to notice here, the mass is the same. Okay, so we can divide out the mass. Next thing we can notice is you multiply both sides of the equation by 2 to isolate the velocity. So that gives you v squared is equal to 2gh because you divided out the mass. Now what you do is take the square root. V is equal to the square root of 2gh. Now that is the basic formula for your final velocity at the bottom. Since you had 0 velocity up here, your final velocity at the bottom is exactly that. Notice it doesn't matter how big that ball is on the pendulum. All it depends on is the acceleration due to gravity and the height and the number 2. Okay, so there is the formula. We'll be using some, and this is the one on page 74, right hand column, near the bottom of that column. All right, so let's clear my writing here, and right here, we'll work right here. Let's do example 3.9 on page 75. A 1 kilogram book, that's the mass of the book, 1.0 kilogram, mass of the book, falls from a height of 1.0 meters. So that's its height of the book, and that's going to be 1.0 meters. Okay, what is its velocity just prior to hitting the floor? Well, the formula we just came up with was final velocity is equal to the square root of 2gh. Remember, that's what we got. Okay, now here's the amazing thing. The mass doesn't matter. There is no mass here. We aren't going to use the mass here. This will be 2 times g. Since this is measured in meters and kilograms, that would be 9.8 meters per second squared times your height. And the height was 1.0 meters. Okay? Now, 2 has no units with it. 9.8 times, well, 2 times 9.8 would be 19.6. So it's the square root of 19.6 times 1 is 19.6. Multiply your units together, meters squared per second squared. Meters times meters is meters squared divided by second squared. Take the square root of that number. Okay, let me pull up my handy dandy calculator here, my phone, and get it in calculator mode here. I'm going to need to turn it sideways to get it so I can take a square root. 19.6 and take a square root of that. If I could take a square root of it. And that gives me 4.42, no, just 4.4, approximately 4.4 meters. And you take the square root of meters squared per second squared, you get meters per second, which is a great unit for velocity. Velocity, I mean, your units are your friends, take care of them. 4.4 meters per second. Now, in your book, they sort of botched up there, at least in my book they did. They said 4.4 meter seconds. It's not meter seconds, it's meters per second. So that's your answer there. All right, do we have time? Yes, we do, to do example 310. Okay, so I'm going to clear my, anyone need this a little bit longer? Did everybody see how you do those calculations? Okay, so let's erase that ink and go back and do example 310. What is the kinetic energy? Here's the kinetic energy. That's the unknown here. What is the kinetic energy? I'm about to drop my calculator. Let me clear it and put it so I won't drop it, my phone. Okay, what is the kinetic energy of a 1 kilogram book? So that's the mass of the book is 1.0 kilograms just before it hits the floor after a 1 meter fall. Well, that 1 meter is the height that it fell from. The height of the book was also 1.0 meters. Okay, now this is an interesting and sort of a dumb little problem. Okay, they do something really interesting here with it. Not quite what I would suggest doing. Okay, now they're wanting to know what the kinetic energy is. Basically, all you have to do is figure out what the potential energy was at the top before you've dropped the book. So let's do, if I could find my, there it is. Okay, let's do the GPE at the top. I'll call this at the top, and what would that be? mgh. Okay, well, the mass is 1.0 kilograms. G is 9.8 meters per second squared, acceleration units, and the H is 1.0 meters. Now that's a pretty easy calculation to make. If I could get my other parentheses to show up here. There we go. All right. 1 times 9.8 times 1, that would be 9.8 kilogram meter squared per second squared. That would be 9.8 joules. If that's the GPE at the top, that's also the kinetic energy at the bottom. Just before it hits, that would also be 9.8 joules. Okay, that's the straightforward way to do the problem. Now here's what they did, and it's sort of nuts, okay? But they did this. They first calculated what the velocity was at the bottom. Well, they used the formula we just had. If I could get my pen to work. Where in the world is the pen now? Can anyone? There it is. Okay, they did the velocity at the bottom to be the square root of 2gh, which is perfectly good to do, but why do that? Okay, so but this is how they get their answer. 2 times 9.8 meters per second squared times h of 1.0 meters. Okay, and that gives us a velocity at the bottom to be, and here I'll go to the calculator. So much harder to do it this way. Okay, get my calculator set up. Like I said, it's sort of crazy. Do 2 times 9.8 times 1, that would just be that. Okay, then I take a square root of it, so I've got to turn my calculator sideways so I can get the square root. There it is. And they get the 4.27. Now here's what they did. This is what makes it crazy. They rounded that 4.27 to be 4.2. Don't round. Don't round. And then what do? The kinetic energy at the bottom, that's what we're looking for, is, let me get my calculator to show back up here. Where is it? My pen. There it is. So the kinetic energy at the bottom, that's what we're looking for, would be 1/2 mv squared. So rather than round this off to 4.4, leave it alone. Leave all those digits on there, and then what you do is square that number. That gives you 19.6, and then you divide that by 2 and multiply it by 1, which gives you 9.8 joules. Okay, what they did when they worked it out, they rounded and it came up 9.7 joules. That's crazy. If you had 9.8 joules to begin with, you have 9.8 joules at the end. So there's a sort of crazy. I would have done it the way we did. Just calculate the gravitational energy at the bottom, no, at the top, set that equal kinetic energy at the bottom, 9.8 joules. Okay, now, enough of that. Let me clear the screen. All right. Let me plug my phone back in, not that I'm in danger of getting too much usage out of it, but we'll all be going to use it later, so let me plug it in just so we have enough energy. Okay, now how are we doing on time? 3 minutes. Okay, that was example 3.9 and 3.10. Okay, all right, the next topic here is energy conservation. And since we only have 3 minutes, and this is going to take a bit of talking, boy, we have more pages than I would like to have had left over. Let's stop there and we will pick up and do our lab next. So let's take about a 5-minute break. Is that okay with y'all? We'll take 3 minutes now, 2 minutes after that. It may take me a little longer to get downstairs. Okay, so let's end this here. I'm going to go to a new share here, and I don't have the right thing up here, but we'll get to it in a minute. So let's stop the sharing for right now. We'll come back to it. All right, so let's take a pause, and I'm going to stop the recording. No reason to record dead time. And I'll go back to Zoom. Okay. I'll go back to share screen. And there's Google Chrome. So I'll go there. All right. Hopefully you can see my blackboard, right? Okay, I'm going to scoop Tobias over a little bit. All right, what we're going to do is go down to this class. Okay, a little bit further down. So here is this class. Going to open it up. It'll open up in content. Okay, now there was our announcement about the meetings. I'm going to turn off my ceiling fan. It just is beginning to get a little cooler. Okay, hopefully that will stop it. Okay, sorry about that. Now we'll go down to weekly assignments, and gonna have to scoot and delete it up just a tad here so I can open this. And
I just turned on my little small heater because the temperature significantly dropped.
yes, it
It's
has.
freezing outside.
I know. My wife was saying that the tropical storm we had go through had it nice and warm, but after that went, we are cooling off quickly. So we're going over the Georgia, this weekend, and my wife said take some flannel shirts because it's going to be chilly over there. The temperature is dropping. So let's go to week 3. I'm going to click on that. That's this week. And then I'm going to scoot up a little bit here. And today we're doing, okay. Go to instructional materials. We did lab 4 on Tuesday. We're doing lab 5 today. I didn't have a place to put it here. So let's go to instructional materials there. And there you see, there's our good old web link to our simulations, and there's the lab. So that's where you'll go to get your lab. I've already opened mine up, so I'm going to the Word document here, and there's the lab. Okay, now I'll start sharing again in a minute. In fact, I think I'll do it right now. Okay, and we'll go back and forth for that one. And I will also go back to the Google Chrome. I think that's what I want. Okay, there it is. So I'm going to click on this just like we've done before. And there is our simulation. So go over here to simulation. When you put your cursor there, it opens up physics, chemistry, and others. We're doing physics, so click on physics. Okay, and this lab that we're doing today is called, I'm going to move Jacob up to the top here. Did you get your PB&J today, Jacob? Never mind, I don't care. Okay, all right. I thought last time you wanted to take a break for your PB&J. Okay, so what we're going to do is go down here to, I think it's called Energy Skate Park. Okay, these are pretty much alphabetical. There is energy forms and changes, which we'll probably do in a later lab. Here's the Energy Skate Park. Now I can't remember if we're doing this one or that one. I think we're doing basics. So let me get that opened up here. Okay. I'm going to have to go back to my thing here and make sure I've got the right one. Okay. All right. Let me see which one of these. It's been a while since I did this one. Okay. Okay. Let's just see what this one does. I think I'm going to have to move y'all again. Okay. I'll move you over here this time. Let me look at the other one. I forgot they had the same names. Goodness gracious, this is a pain in the neck. Here we go. It keeps getting behind the box. Okay, let me go to Here's the one I want to go to. Well, let me close this one out. Okay. Keep going back to the same thing. Ah, here we go. Let's do this one. Okay, go back to simulations. Sorry folks, this is taking way too long. And I don't know why physics won't come up now. There we go. Click on physics and scroll down to energy skate park. All right, let's see if this is the one we want. I don't know what it's asking here. I can't see it. Let me try keep. It sounds like this is not the one I want. Okay. Keep. I don't know. Okay, here we go. This takes longer to open than the other one did. Okay. I think this is the one we want. Okay. Now, I'm going to open this update now. I don't know what this is going to do, but let's update it now. Okay. Okay. All right, here we go finally. Okay. Now, let's go back and forth here. New share. Let's go back to, I think this is the one we want. Go to the Blackboard page for the course. We went there. Go to course content. We were there. Scroll down to laboratory simulations. We did it through, what was it, week 3, and went to the simulations. Click on simulations, then on physics. We did that. Scroll down to energy skate park. Click on download. We did that. When it downloaded, click on it and it will open. Adjust the sim speed to somewhere in the middle between slow and fast. So let's go back here and see if we can find what they're talking about here. Okay. Now, which one was it? This one? Do we have to go through this again? Here it is. Okay. Okay. Now, it says choose a speed between fast and slow. So let's slow this down to about here. Okay. Now, that's the first thing.
I'm seeing a black screen. I don't know about anybody else.
That's amazing.
I'm seeing the same thing.
Okay. Let me see if I can get this to open up. I'm first going to go to here. Okay. You can see that, right?
Yes.
Okay. That's the lab. Okay. It says click on the measuring tape. Okay. It says choose a skater. Okay, we're going to do that in just a minute. Okay, let's go and see if we can choose a skater. Now, I don't know why Yes. Where to find what? Okay. Okay. Let's go back for a moment here. For some reason it seems to have, okay. This is such a pain in the neck, okay, or some other part of the anatomy. Okay. Let's go. I don't know why it disappears here. Now I'm going to do a couple things here. I'm going to try to close. These two are identical, so I'm going to try to, well, I don't know, that's a pain. Okay, let me, okay, I'm trying to see why they are not showing up. I don't know. I'm going to close that for right now. Okay, now I'm going to try to close this one too. I don't think it will. Nope. Okay. Okay. Okay, I'm going back to Blackboard. Okay. Now you probably can't see that. Is that right? Okay. So let's go back to Zoom meeting. See if I can get Blackboard. It's not showing up. So I'm going to close that out again and go back to Blackboard. Okay. And try it one more time. Go to Zoom meeting and share screen. There it is. Okay. Now, can you see that? Okay. I'm going to move this out of the way again. Valerie, you're in the way. Let me scoot you over here. No problem. Okay. Now, here we are in Blackboard. You recognize this? Instructional materials. Okay, week 3, instructional materials. Do I need to go back so you see where that is? Let's go back. Okay, go back one more. Okay, here we are. Here is the class, Physical Science 112, 10695. Okay, feel like the, never mind. Okay, so let's click on that. When it opens up, now I've got to move y'all again. Jacob, you're in the way again. Okay. Let's scroll down here until we hit weekly assignments and activities. Down arrow here, that opens it up. Scroll down here, we're in week 3 now. So click on week 3. Okay. Now, we're in week 3. I'm going to move this. This is such a pain in the neck. It's in the way. Okay. Go down to week 3 and go to instructional materials. You got that? Week 3 instructional materials. When you click on that, here we'll get to labs. Here is the link that we have, the web link that takes us to our simulations. This is the lab we did on Tuesday, lab 4. Here's the one we're doing today, lab 5. Now if you click on the 3 dots over here, it'll say download original file. If you click on that, that original file will show up here in the lower left corner. Wait till it finishes downloading and then click on it and you'll be at that lab. So I'm going to go back to that and you'll see it. I don't know if you'll see it, but I'm going to go there. Okay. And let's see if I can find it. It was just here and now it's not. Okay. So, oh, you did. Great. Super. Okay. I'm going to have to go back to this. Okay. I'm going to have to move this out of the way again. Okay, for some reason mine closed out. So I'm going back and pick it up again. I don't know why it closed out, but it did. This is such a pain in the neck. There we go. You probably can't see what I'm doing, but let me get to it again. Lab 5. There it is. Okay. Now let's go back to our new share, and there it is. Okay. There's where we are. Okay. You see the lab. Now let's see if I can get it to go back to the simulation. I hope that's it right there. There it is. Can you see the simulation?
Yes, sir.
All right. Okay, so it's no longer a black screen. Okay, what we're going to do.
This is not the basics, is it? That's the just energy skate part.
No, this isn't the basic. This is the other one. Okay, because we needed to be able to measure this. Okay, now it says choose a skater. That's the first thing our instruction said to do. Right here, it says choose a skater and record the skater's mass. Okay, so I'm going back to the lab here, and this one's called energy skate part. Okay, choose a skater. Click on this. You see where the little button says choose a skater? Okay, here we have the fat skater. Okay, PHET, 75 kilograms. So that's the one we're starting with. Okay, so let's click on that. Okay, it's chosen, I hope. Choose a skater. All right, let's see if. Okay, that's him. That's the fat skater. So you recorded the mass, didn't you? 75 kilograms? Okay. Now it says, I think the next thing it says to do here is click on the measuring tape and click on potential energy reference and place the potential energy reference somewhere on or beneath the ground and the lowest point of the track. Okay, with the measuring tape, measure the distance between the potential energy reference and the lowest point of the track. Okay, a lot of blah 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 there. Let's see if we can get that done. Okay. Okay, you see them again? Okay, let's get the measuring tape. Okay, and we're going to put this down here somewhere between the ground and the bottom of the track. I don't care where. Okay, if you want it on the ground, that'll be fine. If you want it up here, that will be fine. Okay, now I think what we want to do is measure from the ground. Okay, this is not, okay, no. We need to measure how far it is above the ground. And, there we go. Okay, so we place the little plus here and place the tape here. And we try to get it as vertical as possible. Okay, so looks like to me about 1.65 meters. Agreed? Okay, so that's actually, this might need to come down just a little bit more. Let me see if that does. I don't see that it's moving any. Oh wait, I'm hitting the wrong thing. That's what I want to hit. I can't get the tape to adjust. Okay, we'll call it 1.65 meters. Okay, now what's next?
Click on grid and then click on show
Okay, click on grid. Yeah. Okay. The distance you got is 1.65 meters. Click on the grid, click on the show pie chart. If it's not already there, click on location Earth. Read the acceleration due to gravity on Earth. I hope we know what it is. Let's go back here to Energy Skate Park, and we're going to choose. Okay, let me see. Did I skip this one? Ah, there it is. I think that's what we messed up before. Okay. Okay. There's your potential energy. Okay. We're still going to use 1.65. Okay. Check on grid. Okay. Now, oh, show pie chart. That's the next one. Okay. Now, okay. What this pie chart is showing is the blue is potential energy. And you see when it's almost all blue, that's when it's at the maximum height. Almost all blue is maximum height. The green is kinetic energy. Okay. It's the maximum green when it's right here at the bottom. See, it's increasing green, increasing, decreasing, decreasing. Okay. Now the reason it doesn't completely get rid of blue, you still got some potential energy here because you're 1.65 meters above the reference level. Okay. Now, okay, what's the next thing it says to do?
If it is not already there, click on location Earth, which it was already there.
Okay. All right. Oh, that's right. I remember that now. So, okay. There it is, location Earth. It says what's the gravity there? Acceleration due to gravity, 9.81. Now they use a term unit of newtons per kilogram. We've been using meters per second squared. I like meters per second squared better, but whichever one you want to use. 9.81 meters per second squared. Okay. Now, what's next?
With the measuring tape, measure the distance between the potential energy reference and the highest point the skater reaches on the track.
Okay, I'm going to have to move y'all out of the way again so I can read this. Okay, with the measuring tape, measure the distance between potential energy reference, that's that dotted blue line, and the highest point the skater reaches on the track. Okay, so let's go to back here. So let's take the measuring tape here, and we're going to go up as high as he goes, right about. Let's see if we can pick where he goes to. I don't know which side is better to go to. That looks about right. Now let's take the thing and measure how high above the zero reference level he is. Looks like about 5.41 meters. Agreed? Yay or nay?
Yay.
All right, yay. Okay, let's see what's next. Okay. Okay, potential energy at the skater's maximum height. Remember what the formula for potential energy is? mgh. The mass was 75 kilograms, right? Now, the potential energy at the skater's maximum height would be mass, 75 kilograms, times G, we're on the surface of the Earth, 9.81 meters per second squared, and then what was the other part? H, and that was the height we just calculated, right? Y'all wrote it down, right? I don't. Okay. Okay. It says calculate the you wrote this down. How high is the highest point you reached on the track? Was it 5.41 or something like that? 5.41. Okay. So calculate the potential energy at that maximum height. PE or GPE is mgh. The mass was this up here, which I think was 75, wasn't it? Okay, 75 times G, which we had was 9.81 meters per second squared, right? Okay, and then the height was 5.41 here, right? So let me get my handy dandy calculator and see what we get there. Okay, y'all have to remind me if I'm doing it right, because I'm doing from memory. I don't have it written down. 75 times 9.81 times 5.41. 5.41 equal. Okay, that looks to be about 3,980 joules, right? That's going to be your potential energy measured in joules. Is that what y'all got? I may have punched it in wrong. It seems like a... Is that what you got?
Yes. Yes.
Okay, good. All right.
What was it? I'm sorry.
Okay. Oh, there it is. Three 3,980 joules. That's what you said you got to, right?
Yes.
Okay. So that's your answer to potential energy at the skater's maximum height. It says determine the speed at the maximum height. What you think that is?
Let me guess. Nothing percent.
You're absolutely right, because the speed, see, it's decreasing, maximum height, the speed goes to 0 right there, but then it starts picking up again. So the speed at maximum height, can you see this on your screen? Up, not quite. Okay, let's go back to here. Okay, determine the speed at maximum height, 0 meters per second, right? Determine the kinetic energy at the skater's maximum height. Guess what that is? Kinetic energy is 1/2 mv squared. If the speed is 0, kinetic energy is 0, right? Yay or nay? All right, yay. All right. Calculate the mechanical energy at the skater's maximum height. Does anyone remember what mechanical energy is? It's the sum of potential energy plus kinetic energy. Well, that's just going to be, since kinetic is 0, it's going to be your potential energy, whatever that was. You just, oh, it's still on my screen here. 3,980 joules, right? Okay, that's your mechanical energy at the skater's maximum height. Okay, now calculate the potential energy at the skater's minimum height. Okay, now remember right here, measure the distance between the potential energy reference, measure with the measuring tape, measure the distance between the potential energy reference and the lowest point on the track. That's going to be at its minimum height. So calculate potential energy at the minimum height. Y'all wrote it down, right? What was that distance here? Wasn't it something like 1.65 or something like that? Okay, so we'll calculate the potential energy there. So its mass was 75 mg times 9.81 times, and what do we just say it was? 1.65 equal, I got 1,214 joules. Okay, so that's the potential energy at the skater's minimum height. Now why is it there? Because the track was above the zero reference level. Okay, determine the mechanical energy at the skater's minimum height. Well, mechanical energy is the sum of the potential energy plus, I'm sorry. Mechanical energy is the same throughout because energy is conserved. So the mechanical energy at the maximum height is the same as the mechanical energy at the minimum height because energy is conserved. Mechanical energy is conserved. So whatever you had for here, you have down here as well. I don't remember what that was. Perfect. Okay. Now, what would then be the kinetic energy at the skater's minimum height? Well, kinetic energy plus potential energy equals mechanical. So therefore, if you have the mechanical energy, subtract from that the potential energy, that gives you the kinetic energy. So I think we had 1,214, okay, and then add to that, what was it, 3,980? Was that it?
Yes, sir.
Okay, and what do you get? The kinetic energy, look,
Difference between the two, right?
difference between the two, right?
2,766.
Perfect. 2,766 is the kinetic energy at the skater's minimum height. Perfect. Now, how are we going to calculate the speed at the skater's minimum height? Okay, now I don't think it lets me write on this screen. I'm going to try to, but I don't think it will. Okay, let me see if it will. No, it won't let me write. Okay, sorry about that. Okay, what I'm going to do is go to the whiteboard here. Okay, and here's the whiteboard. Now I've got to move some things around here, so hold on just a minute. Okay, and I think I'll just move this up and over to the right as much as I can. Okay.
Is it okay that we put notes on our labs?
Absolutely. I think that would be preferable. Okay, now what do we have? Kinetic energy, which you know what it is, right? You just wrote it down. 2,766, is that right?
Yes, sir.
Okay, that's equal to 1/2 mv squared. This is the maximum velocity at the bottom. This is kinetic energy at the bottom. So we have, let's solve this for velocity here. So first thing we're going to do is multiply everything on both sides of the equation by 2. Okay, there we got rid of the 2's. So now we have mv squared, I'm switching sides, is equal to 2ke. Okay, Now divide both sides by m. Okay, you get rid of the m's. Now we got v squared is equal to 2ke divided by m. And what we're going to do now, take a square root of both sides. So now we've got v is equal to the square root of 2 times kinetic energy divided by m. So let's plug in what we know. The square root of 2 times 2,766, 2,766, isn't that what we had?
Yes.
And that was kilogram meters squared per second squared. That's what a joule is. Okay? Divided by the mass was 75.0 kilograms. So the kilograms go out, and so there's your answer. 2,766 times 2 divided by 75 equal, and I get 73.76, and now I need to turn it sideways so I get scientific notation and take a square root of it. So what is the velocity then? I got something pretty close to the 8.59. And what's the units? The kilograms went away, and the square root of meters squared per second squared would be meters per second. An excellent velocity measurement. Did y'all get that too, or did I make a mistake with my calculations?
I got that.
You did. Okay, that makes me feel nice and warm and fuzzy. Okay, now, so that is what we put. Let's see if I can do this. Okay, go back to our board here, and that was our calculate the speed at the skater's minimum height, and that was about 8.59, right? That's what goes here. Does everybody see that? Yay or nay?
I'm sorry. Say that again. I'm sorry.
Okay. We calculated the speed at the skater's minimum height. Here's where we did it. I'll go back to that, the whiteboard. And that velocity was the square root of 2 times kinetic energy at the minimum height, which is there, divided by the mass, which is there. You do 2 times this, divided by 75, then take the square root of that, and we get 8.59 approximately. Okay, that's what we write here.
That's the speed for
Speed at the skater's minimum height. Make sense?
yes.
All right. Let's go and see if we get anything close to that. Okay. I don't think it shows us a velocity there, so we'll just have to take our own word for it. Okay. So where do we go next? Okay. Scroll on down here. Choose a different skater. Okay. Now you get to choose any one you want to, but let's see. Here is our energy skate park. So choose a different skater. And you want to do star skater? Yay? Okay. Oh, you want bulldog? Okay, whichever you want. Y'all want bulldog? We're going to do them all, by the way, so it doesn't really matter. So bulldog's going to be 20 kilograms. Okay? So there's the bulldog on here. Okay? There's a bulldog on the skater thing. Okay, now let's go back here. 20 kilograms, didn't we say? Okay, choose a different skater. You chose bulldog and record the skater's mass, 20 kilograms. Let's calculate the potential energy at the skater's maximum height. Okay, now remember what potential energy was? mgh. M now is 20 kilograms, right? G is 9.81 because I think we're still on the Earth. And the maximum height was at 5.41 or something like that?
Yes.
Okay. Okay, I believe that's the same location. Let's just check it out and see. Yeah, the bulldog goes right to the same height, 5.41 meters. Okay, so, okay, potential energy at the skater's maximum height would be 20 kilograms times 9.81 meters per second squared times, was it 5.41?
Yes, sir.
Equal
1061
1061 joules. Joules, got it. Okay, don't ever just put a number, always have that. Okay, so there's the potential energy at the skater's maximum height. Determine the speed at the maximum height. Remember what that was? Zero. Excellent. Determine the kinetic energy at the skater's maximum height. What was that? Zero. Determine the mechanical energy at the skater's maximum height. That would have been, since the kinetic energy is zero and mechanical is potential plus kinetic, whatever your potential energy was here, that's your mechanical energy down here, right? So whatever you figured that was, I think it was 1061, wasn't it?
Yes,
Joules. So that's the mechanical energy at the maximum height. Now, the potential energy at the skater's minimum height. Remember, that again was no, wait, not yet, not yet. Okay, you have to calculate this one. This is mgh, where m was still your 20, right? Times g was 9.81, right? Times, now we do the h. Remember the h at the minimum height? That was up here, 1.65. Yes, times 1.65. Equal what you have the potential energy at the minimum height. 324. Excellent. Excellent. Does everybody see that? Okay, that's potential energy at the skater's minimum height. This is the bulldog's minimum height. Determine the mechanical energy at the skater's minimum height. Now this is the one, remember, mechanical energy is always conserved, so whatever the mechanical energy was at the max, that's the same mechanical energy at the minimum. So whatever you had here, I don't remember what it was now, you put the same number here. Mechanical energy is conserved. You got it? Now comes the difference. Okay, the kinetic energy at the minimum height is mechanical energy at the minimum height minus the potential energy at the minimum height. So I'm going to negate that and add to it. I don't remember what the mechanical energy was at the minimum height. Does anyone?
It was 1061 minus the potential energy, which was 324.
Okay, so what did you get?
737 joules.
27 or 37?
737.
37. Okay, I must have punched it in wrong. Okay. Okay, so that's the, did everybody get 737? I must have punched my numbers wrong? Yes or no? Did y'all get some? Okay. Now that's the kinetic energy at the skater's minimum height. Now we go back to what we were doing before on the whiteboard, and we do the same thing, except we're going to solve this again. V is equal to 2 times whatever that kinetic energy was divided by m. So let's do this in a different color. Do y'all have a color preference? Okay, I'm going to do red. Okay, so now this is V for the bulldog, okay, is equal to the square root of, same thing as we had here, but it's 2 times the kinetic energy of the bulldog divided by the mass of the bulldog. Okay, now y'all have to fill me in on what those numbers are. I know what 2 is. What was kinetic energy of the bulldog at the bottom?
737.
737.
Divided by
20.
20.
Okay, so that would be about 73, I believe it is, 73.7. Okay, and then take the square root of it. Okay, yuck. 73.7. Nope, it didn't take. Yuck.
Almost the same.
What's that?
I calculated that wrong.
What's that?
Were they almost the same? I got 8.58.
Okay, let me see if I can write this down and do a square root of that.
Or 8.59.
I got 8.582. So the velocity of the bulldog, guess what? That's also approximately 8.58. In fact, it's close enough for government work, 8.58. Just round off error. And that would also be meters per second. Well, guess what, team? Remember, it's irrespective of the mass. The mass doesn't matter. Remember, your V, now this isn't quite the same thing, but V at the V final was equal to, now we can't use this formula here because we weren't at the bottom, okay, but that is 2G H. Mass is not in the picture at all. So sure enough, we expect the velocity to be the same. This was the velocity of the, what was that guy called? Whatever. Say again? Oh, that was the PHET, P-H-E-T. Okay. And this is the bulldog. Okay. So it doesn't matter the mass. Their velocity will be about the same. And when you look at this, they look like they're going about the same speed, right? Now you can't go by looking, but there's the bulldog and here's the PHET skater. Don't they look to be going about the same speed? Okay, good deal. All right, so let's go to back to our sheet here. Okay, choose a different skater. Who you want to choose this time? Okay, let me find them again. Choose a skater. And what did you want to do? The ball? Is that the one you said? Okay, that would be 5 kilograms. So write that down. Choose a different skater, the ball. So let me click on the ball and do OK. And there the ball, you see it goes up and down. Boy, our thing here has gotten really small though, hasn't it? But we know what's going on there. Okay, so let's go to our, now what was that again? I can't remember. What was the mass?
Oh, 5 kilograms.
5 kilograms. Okay. I have a good memory. It's just real short. Okay. Okay. Choose a different skater. Y'all chose the ball. You can write that if you want to. Record the skater's mass, 5 kilograms, right? Okay. First is calculate the potential energy at the skater's maximum height. Okay. And it went right back to the same height. So that is going to be, now I can't find what I did. Oh, there's my calculator. Okay. The potential energy there is mgh. So that's 5 kilograms times 9.81 times, was it 5.41? Is that right? Is that right?
Yes, sir.
5.41 meters. And that gave us a potential energy at the maximum height of, is that pretty close to 265? Yay or nay?
Yes.
Yes. Okay, 265 joules. Okay. Determine the speed at the maximum height. Remember what that was? That's exactly what you got. Okay. All right. That's 0. Boy, I've been sitting too long. I have a dead end. Okay. Calculate the kinetic energy at the maximum height. 0 again. Okay. So the mechanical energy at the maximum height would be kinetic, which was 0, plus potential. So it's all that potential. What was that? 265 joules? Okay. So that's going to be your mechanical. It's going to be 265 joules at the maximum height. What is potential energy at the skater's minimum height? Okay. Wasn't it 5 kilograms?
Yes.
Times 9.81? 1.65. Y'all are remembering this really well. So 81 joules. Okay. That's potential energy at the skater's minimum height. What was mechanical energy at the skater's minimum height? Exactly what it was at the maximum height. Okay. So what's the kinetic energy at the minimum height? Okay, let me make sure I get this on the screen here. We're going to negate that and add to that, what was it, 265?
Yes, 265.
Okay, so what is the kinetic energy at the skater's minimum height? 184 joules. Okay, now we go back to our whiteboard. If I can get the pen to show up somewhere here, there it is. Okay. Okay, go back to the whiteboard. All right, let's choose a different color here. Well, I've already used red. The ball was red, so let's do sort of this brownish color here. Okay, so oh, that was a bulldog. Okay, now we're doing the ball, which is also starts with B. So if I could get, oh, no wonder I can't write on my calculator. I write on the pad. I had the wrong thing in my lap. Okay, where in the world is my, there we go. So this is the velocity of the ball, not the, whatever the other B was, bulldog. Okay, this would be the square root of 2 times, was it 184? Yep, 184, or 184 divided by 5. Okay.
I got 8.579 rounded over to be 78. I mean
Okay, take a square root again, and sure enough, we're right back at 8.58. Is that what you said?
Yes, sir.
Okay, that's what I got too. Approximately 8.58 meters per second. Right about the same as here and the same as there. Within 100th of a meter per second. Guess what? That's close enough for me. Okay? Everybody got that one? All right. Any questions? All right. Speed of the skater's minimum height, exactly what we had before. And guess what, folks? I think we've run out of lab. If you wanted to go back, you can, and go back to and do another skater. You could do star skater at 60 kilograms, or you could go to the bug at 0.2 kilograms. Anything you want to do, knock yourself out. Any questions? You okay with it? Any questions?
No.
All right, good deal. I feel like I'm cheating you out of your tuition dollars because we're finishing this almost an hour too soon. Do you want to do some more? No, I can't believe that. Okay, but you certainly can now if you want to. Okay? What's that again? Are y'all talking to me or to one another?
Look like they're talking to each other.
Okay, all righty. All right, to shut it down?
I'm good.
Okay.
You gotta say, those are some frictionless skaters. Absolutely. No song.
Yes, exactly. You would think they'd get tired after a while, wouldn't you? But that's because we're assuming zero friction. Not a good assumption, but for the purposes of this lab, perfectly okay. All right. Any other questions, issues, concerns, problems? Okay. Then what I think I'll do is end the recording. Okay, you ready for that? Okay, we'll end the meeting for us all. And folks, I'm going to say it again. I think I said it early on. Have a good weekend, which means a safe weekend. It's going to be a little cooler, so don't go out there trick-or-treating too much because COVID is still out there big time. Okay, be careful. Be very careful. The other thing is, next Tuesday, what day is that? Voting day. So if you haven't voted already, which many of you may have, I know my wife and I have, and some of you may not be able to vote. I understand that too. But if you can, you're registered to vote, please vote. Even if it means missing a little bit of this class or some other class, or I would say this one, don't miss another class. But if you can do it without missing class, that's even better. So take care, folks. Have a good weekend and vote.
Thank you.
Thank you. Bye-bye.